Hi. Thank you so much. No. Good morning, everyone. Thank you for attending this morning session. Thank you also to Durian Pai for giving me this opportunity again for the second time because I am the speaker for the last year. No. So, yeah. Unlike Mr. Valdez, who has coded with fearless passion, I play safe for this year. So I don't have any live demos, right? So yeah, for this talk, we'll be making a programming language for fun using Exec and Tree-Sitter, okay? So yeah, but before we start, um, fun fact about me, yeah. So hi, my name's Ned. I am based in Davao City. I'm currently a software engineer at Betterteam. We are a startup based in Australia that builds application tracking systems. Fourth, I'm the committee lead of. I wear many hats, but I'm currently the committee lead of PWA Pilipinas Davao. And just to give some kind of credibility to my talk, I'm a former core team member at a programming language that I cannot say, but it starts with letter V. I am working on developer tools, okay? And lastly, I am a father of 120 abandoned repos. Okay, so yeah, just a bit of interaction. No? So, who among you are computer science students? Raise your hands. Who among you have their programming language class? Okay, so what's the one word you think of when you hear the programming language class? Is it is it pain? Is it sadness? Is it whatever negative connotations you have, right? Whatever you think about that subject, it's gonna be a pain to your student life, right? And yeah, I can relate to that as well. No, so but given that I have some experience working on projects before, I realized that there's fun to it. That the in that something that the classes cannot do, right? And for me, learning programming languages should be fun because for me, learning how to do things, how to dissect how it works, makes you a better programmer. No, so yeah. So in the next 20 minutes or so, we're gonna be tackling all this lives out process of developing a programming language, except for the semantic analysis, of course, because it's gonna be time consuming. Okay, so yeah, so we'll have the five, and the first part of this is what we call designing. So yeah, before we are able to code on our first ever compiler or interpreter, we need to design how are we going to express the code that we want or the application that we want to build, right? So here, this is the first step in our programming language making process. Okay, so when you're going to decide, you're going to make a rule. Okay, so rules are just patterns, right? Sequence of words or characters. And once you're able to define a set of rules, you're able to create a so-called a grammar. Okay, similar to an English language. English language has these rules, of course, on how to create a cohesive sentence, a valid sentence, right? Similar to a programming language as well. So here, we're going to build a grammar. And if you're going to define the behavior of how that specific rule works, you're also going to be able to build a so-called specification. No? And you might think of yourself, where do I start? No? Because there's lots of ways to think of or to build a grammar. So for you to not really use to exert much brain power, so you can start with an existing programming language. And in this case, we're going to use Python, right? And because Python, we're in PyCon, so we're just going to be Python, right? So yeah, so for example, in this session, it's not going to be a lot of code because of time constraints, of course. So we're going to be focusing on declaring a variable and calling a function, okay? And here, you can just simply find and replace the Python code as your base, right? So you can just replace indents with braces. You can just replace it with keywords such as def, or you can add new syntaxes to suit your liking, no? Inspired from other languages. But yeah, in my example for today, we're going to build a language called script. I know it's a meme, and I don't know what Stana means. I just picked it up yesterday, what that means. So yeah, so this is a syntax we're going to build. Okay, so our variable has this keyword, and then we have, if we're going to call a function, there's going to be a dog in the end. Yeah. Okay. So now we are able to create our own language, our own syntax. So we're going to dissect it now. Okay. So again, that's the reason why we have a simpler example is because once we're going to dissect it, it's going to be a lot. Okay. In this example, we have 5 rules we're going to build. Okay, we have the string, identifier, concatenation, function call, and variable declaration. Okay, and once we're able to dissect it, we're going to create a pseudo grammar. Okay, so I really don't listen to the class at all. So I just made my own way of expressing my grammars. But what's important here is you're going to document the patterns that you're going to build in the next few minutes in this journey that we're going to have. Okay, so let's proceed to lexing and parsing. So lexing and parsing are 2 stages that converts the text that we have into a machine-readable data structure. So the first one, lexing, is just breaking down this set of this text into multiple words and characters of what we call tokens. Okay, so you might heard tokens in AI space, but in programming languages we also have tokens as well. The similar concept. In parsing, so once we're able to lex this plain text into a series of tokens, a set of tokens, we're going to now consume it through this process called parsing. So parsing, it converts a series of tokens into a well-structured data structure called AST, or the abstract syntax tree. So as visualized on the picture of the right. Okay. Just to further give you some understanding of what is this, no? So we have here a sentence, a plain English sentence. Ned is dancing. Okay. So with lexing, we split the words into spaces. So here, and then we are also going to be categorizing it at the get-go. So first, the first 3 are the words, and then the period is a punctuation. Now, how are we going to do it how is it going to be the result when it comes to parsing? So in parsing, we're able to identify the patterns here used in our grammar. So in this case, the first word is a subject, and then if we combine is dancing, that's a predicate, and then in the end, we have the terminator, which was the period punctuation. And then if we package it all, it's going to be categorized as a sentence, right? And established programming languages like Python, they use handwritten parsers or lexers to be able to decode the code into a program, right? But if you're able to create a project like this, it consumes time, right? So it can be, if you're starting to explore, it's not gonna be worth the time if you're going to consume the time just for this. So we have these tools called parser generators. We have lots of parser generators out there. There's Antler, for example. But in this case, we're going to use TreeSitter, okay? Because TreeSitter is like the one I've used in our project last time. So I'll give you a brief introduction. TreeSitter is a parser generator created in 2018 for the Atom editor. So if you are able to code in GitHub Atom editor, so this is the one that powers the highlighting and everything. So it provides a syntax tree structure that's error tolerant. Second is easy to maintain. It's JavaScript based grammar file. Yeah, and it's primarily aimed for text editors, but in this case, we can also consume it for the compilers and interpreters as well. Okay. So to get started, first we need to have Node.js. I know it's Python, but it's Node.js, and also a C compiler for this because we're dealing with a parser, right? And just follow the instructions in the link that is given there. Okay, now let's set up our workspace. In this case, we're going to have two files or folders. First is the main.py, it's a program we're going to use later, followed by the tree-sitter, which is our parser here, tree-sitter script. And yeah, that's basically it. Now let's proceed to creating our first tree-sitter parser. So we're going to navigate to the tree-sitter script folder. Just do tree-sitter init. You need to fill up the details. Then once you're done, you're going to have a file that is so-called grammar.js. Okay? So the grammar.js is a way for you to specify the grammar that you're going to create for the parser. Okay? So here it's gonna be long. I know it's readable there, but yeah, so I never thought it was gonna be readable here. So I'm going to just give you a quick tour on this file. So for this one, we have three inputs here. We have the parser name, we have the extras, and the rules. For the parser name, it's self-descriptive. It's going to be the name to be used for identifying the parser. Second is the extras. Extras are the tokens that are expected to appear everywhere. But the problem here is that you need to specify, if you don't specify the white space here, it's gonna be a hassle for you to declare your grammar rules, right? So extras gives you a way for you to just skip this specific token and just directly describe what you're going to say. And then rules is where you describe the grammar you've created earlier, right? So yeah, for the rules, it's going to be an object, which contains a pair. First is the rule name, and then followed by the rule value, which is a function here that is that has a $sign parameter for referencing other rules. And if you're going to name it with an underscore as a prefix, it's going to be what we call an anonymous rule. So it's not going to appear in your tree, but it will directly reference the children or the child to your directly to your parent. I'm just going to have a quick scheme here about this, but basically we have functions for expressing how the patterns or how are we going to declare our grammar. So first is a seek. This is a seek function. From the word itself, seek, it's a sequence of tokens followed by a field. So field is a way for you to internally tag your tokens or your the structure of your rule, so that you'll be able to access it later on once you're able to traverse it. And then you have the choice. Choice means the parser can pick one of the many rules that you're going to declare there. So for example, if a program can pick either a variable declaration or an expression, and we have the repeat here from the word from yourself repeat. You'll be able to match 0 or more nodes here. So it's not just one node, but you'll be able to have a children of nodes in just that one rule alone. And we also have regular expressions. I know you're scared of regular expressions, but here it's part of how are we going to identify the patterns here. In this case, the identifier, we have an A to Z, an alphabet and an underscore that is going to be identified as an identifier, okay? Oops. And then we also have the prec for the precedence. So if you know MDAS rule, so MDAS, you prioritize multiplication, division, addition, subtraction, right? Here we did do this as well. So precedence is a way for us to solve the ambiguity by giving one rule priority over the other. So in this case, in our concatenation rule, we are going to group the nodes on the left instead of the right. Okay, if you're going to have multiple nested concatenations out there. Now, let's try our tree-sitter parser by basically going to our folder again. And then we generate first the parser. And then, since we're using Mac, I'm using Mac here, I can just use my standard input as our input for our three-seater parse. So when we do three-seater parse here, using this one, our input, then it will show here the abstract syntax tree. Okay? So in order for us to use the three-seater parser in our Python program, so we have the official bindings for the Python, for the three-seater in Python. So this is what we call PyThree-seater. So it allows us to consume our three-seater parser that we did in Python. Okay. So for this, we're just going to initialize the virtual environment for this and install three-seater. And then here, what's important here is that you need to also use pip install for our three-seater parser, because since we have a C code in there, our native code in our Python, in our three-seater parser, so Python will be the one building it into a Python binding as well. And then we're going to consume it in our main.py. Okay. So this is our import statement. We load it with our parser, and then we have the input as a bytes. And then we just print the root node for this. And once we run it, it's going to be an abstract syntax tree similar to the one you've seen earlier in three-seater parse. Now let's proceed to code gen. So code gen is the last stage in the compilation process, right? So it translates the abstract syntax tree that we have into a machine code that the CPU can execute. So most common target for this is assembly, and most commonly it's going to be the ones in your computer, so x86 or ARM, okay? But it's a pain to program. I don't know assembly that much, so we're going to resort here to what we call transpilation, and we're going to use Python instead. So let's assume that that CPU runs Python. So here we're going to have a function below it. So we're going to comment the print statement that we have, right? We're going to build a function called CodeGen, in which here, this is a recursive function that traverses our AST. And then here, we're going to have a match statement that will match the rules or the node type, in this case, of our target node. So since our root here, if the root here is program, so the first one will be matched, right? And then followed by the children here, which is the variable declaration in the function call. So the next ones here will be matched here as well, and it will generate a Python code, right? So once we're able to traverse all of the nodes in the tree, it should be able to give you back a complete Python code below here, which is the print. So here, once we are able to execute it, it's now a Python code, okay, which is, it's where this is going, right? And this is where we go to our last step, okay? So this is now the happy face part of our process, which is executing. And executing, exec, so dynamically, Python is a dynamically interpreted language, right? And they provide tools for executing dynamic generated code. So for example, JavaScript uses eval, Ruby provides kernel.eval, and then third, Python provides what we call the exec function. And then exec function is just built in Python. You don't need to import it in the standard library. You just kind of just call it similar to print, right? And basically, we're just going to replace this one with print with exec, okay? And once we're able to replace this one with a simple one-line code change, bada boom, we have able to run a Python program using our own language syntax, right? Yeah. Walang live demo, guys, but just a short. But yeah, that's actually the actual output here. So yeah, the takeaways here. So first is that you don't need to build everything from scratch. You need to leverage existing tools and host languages to prototype quickly. So you don't need to be able to write your own parser, lexer, and everything just to be able to create your own language. Second is that language design starts with grammar rules and define patterns before worrying and implementation so that you won't be able to have your head explode, right? And then third, transpilation to an existing language is a valid alternative to compilation. So it's faster to prototype and easier to maintain. And lastly, making a programming language is more accessible than you think. Modern Turling has lowered the barrier to entry, as we've seen here with TreeSitter and Python. So I can just check the code in my GitHub, and then you can just connect with me in my socials. All right. So thank you so much for listening.